So good afternoon. You can't believe how happy I am to be here. When John called me and asked if I would be willing to do that, I hesitated about a nanosecond because I owe so much to Roy. Roy is the person who's really, more than anybody else, changed my life in physics. I remember when I was a grad student in Switzerland in 2004. No, in 1972, I was really interested in quantum optics, and we'll get back to that later. My supervisor was a very wonderful person, but he was a condensed matter person. And he didn't think that it was the right topic for me, but I really wanted to do that. So I decided to write to Professor Glauber. I told him, I want to study with you. I want to come to Harvard and be your student. And he explained to me that's not quite the way it works. But fortunately, he was going to be at CERN that next year, which is just 40 miles from where I studied. So I went to meet him with my supervisor, and we started to talk, and he was kind enough to not say horrible things about what we were doing. I bribed him by introducing him to something which is called the colonel. You may not know what a colonel is, but it's lemon sherbet and vodka. So this helped. And to reward me, he then sent me to Scully. So I never made it to Harvard, I made it to Tucson, where Marlon Scully was at the time, and then I went to Munich and then back to Tucson, and we've been really, really good friends ever since. So it's really such a pleasure to talk on your birthday, Roy, and I hope that Marlon will forgive me for having ruined his life to the point where he had to move to Texas. All right, so this is about quantum optics. So and John also told me, oh yeah, you could maybe try to give a little bit of a survey of what Roy's impact on quantum optics has been in the last 50 years. And I thought it was a great idea until I realized that it's a full errand because he's done so much that there is no way you can talk about it all in 40 minutes. So what I will do is kind of cover a few things very, very superficially, show how it started with Roy, and just pick up a couple of examples of where this stuff has still an enormous amount of influence right now. So we're going to go back and forth in time a little bit. And hopefully I will not lose you too much in the way. And I will try to keep the equations to almost zero. Not quite, but almost. All right. So this is how it started. This is why I wanted to study quantum optics, because I had put my fingers on this book. And I think that everybody who is older than, when did your book come out? 74? Sergeant Scully Lamb? So before that, that was the book where one learned quantum optics. And it's a fantastic book. And Roy's article is really, it has everything, and I always show this work to my students on how to write good papers. Okay. And I wish I had been to this school, because this collection of speakers must have been absolutely spectacular. But anyway, I didn't go there. But that was the Bible of quantum optics, and in many ways, I think it is still the Bible of quantum optics. One still has to go there to go back to the roots. And I was actually in Lelouch this summer, and I was talking to the people because I knew I would have to give this talk. So I was trying to dig some dirt on Roy. And I didn't find a lot of dirt, but what they told me is that at the time the accommodations were not quite what they are now. And this is kind of where the lecturers were staying, right?
Just one.
And this was for one or for all lecturers? But also, it never became completely clear to me if you stayed in this one or in this one. So that's the one. That's the one. Okay. So these things, many of you, I'm sure, have been in Lelouch since then, and it's really luxury accommodations in comparison now. And the other thing is that I tried to find a picture from Lelouch in '64, but all they could find in Lelouch is this picture, which is not very good. And here is Roy, and this is Fermi, right? And it was in '54. This was another school where you were talking about nuclear physics, I imagine. I don't know who that is.
John Hughes was at the cosmodrome with
Okay. So anyway, so that's historic picture. which I'm sure we'll see 3 more times. All right. So how did it all start? How did quantum optics all start? It started with this paper, really, a test of a new type of stellar interferometer on Sirius by Henry Brown and Twist. And now everybody knows Henry Brown and Twist. Many young students think it's 3 people, but no, it's 2 people. Okay. And what they did is that they actually had this interferometer where instead of combining 2 electric fields, they just looked at correlations in the intensity. And I've taken some stuff from the original papers. I hope everybody can read it in the back. I hope it's not too small. But here is what they said. They said that in this instrument, the signals from 2 areals, one A and A2, are detected independently, and the correlation between the low-frequency outputs are recorded. The relative phases of the 2 signals were lost, and only the correlations of the intensity fluctuations are registered. Okay? So it was really a new way to do astronomy, and it got everybody crazy because nobody really understood how to interpret these results very well. People knew how to do a Young interferometer, traditional interferometers, but they didn't really know how to deal with that. So basically, suddenly, quantum optics started because of issues in coherence. How do we deal with these kind of problems? And for several years, the situation was as is summarized here. Okay? So everybody was in the dark. Nobody knew what to do, and there were all kinds of question marks. There were theories which were mostly wrong and mostly not doing a job very well, which led to predictions which later it became quite clear that they were actually not reliable, not correct. But this is an allegory also, because you see there is light coming. Okay? And the light came this way. Okay? The light came with this paper. Okay? These are letters, by the way. Just saying, okay? This is an absolutely fantastic paper, okay? And every student should really read this paper. It has so many important things. The first thing that he does, he says, we have developed general quantum mechanical methods for the investigation of such correlation effects and presents results, specific results here. And then it goes talking about the optical maser. We'll get back to that in a minute. I'm not going to concentrate on it here. He does say that these predictions were misleading. And then he says, in considering the problems, we shall outline a method of describing the photon field, which is particularly well suited for the discussions of experiments with light beams. And this was really new. This is just not the way people were doing optics at the time. So this was really an incredible breakthrough. And basically, it brought to the front of the discussion the point that you have to talk about correlation functions of the field. Okay? And here is the thing that everybody in this room knows for sure. It says, the states we wish to describe include states in which the phase of the mode is reasonably well defined. So you don't want to use number states. And, you know, Fock states, everybody used to use, if you look at Heitler's book, does anybody know Heitler's book? You guys don't count. Right? It was not all about Fock states, all about the eigenstates of the energy Hamiltonian of the light field. And here came Professor Glauber and says, no, don't do that. Okay? Use fields which take into account the phase of the field, so make coherent superpositions. And why he came with this one, I'm sure that we'll hear a lot more about that. I'm not going to go into many details. I know Serge's talk will talk quite a bit about these so-called coherent states. That's how they are called now. And I have just one pretty picture here which shows that the coherent states are eigenstates of the harmonic oscillator. Right? And this is one of the key reasons why these states are so absolutely important. Okay. So this paper is absolutely key because it really totally changed the way we were going to talk about light fields. Okay? And it's everybody who does quantum optics uses these basic ideas in one form or the other these days still. I do have 2 hours, right? Where is he? He left. Oh, no, he's here. Remember, I'm the editor of Physical Letters. Okay. So now, let me get back to the state of the maser, okay? Because that So it started with Humbury, Brown, and Twist, but in 1960, the optical maser was invented, and people started to worry about what is this beast, what does it do? And nobody really knew very well. But Roy started to think about it, and here, again, I've taken out of his papers something. On the other hand, a maser is not at all likely to be described by an incoherent classical model. So there was a debate about how you describe a laser, and nobody really knew. Okay? And he actually had this beautiful hindsight that more plausible models are much closer in behavior to the ideal coherent states. Of course, it was not a theory, it was kind of mostly a guess right at the time. But what happened then is that people started to do more experiments. And I'm just, oh, and there was a series, there was a group, which university? It's not Harvard, it's Yale? Yale. Yes, so there was a group at Yale which actually worked on the theory of the laser. Okay. And here it is. Do you remember that?
MIT.
and here is a beautiful curve which shows the photon statistics of the laser below threshold and at threshold and above threshold. And then a curve which shows the laser slightly above threshold. It's only 20% above threshold compared to a coherent state. So it was not quite a coherent state, but it was quite close. And far above threshold, we all know that it goes to the photon statistics, the Poisson photon statistics of a coherent state. And the beauty is that there were also some experiments which were done. We already mentioned the Humbury-Brown Twist experiment, which now was understood dealt with thermal light. And then there was this a paper by Tito Arecki and his co-workers in 1966, where they did G2, they do intensity correlation functions for thermal light and for a laser field. And they found that for the laser field, you get the result of a coherent field. And here I have a bit of a question, because if I go back to the previous slide, right here, this is in 1967. This is a question from Alan, right? And these results were in 66. So did you know this? Did these results go all the way to Yale?
Well, the first paper was 65, our first paper.
So I got the wrong paper?
No, it's okay. The editor of Physical Writers can do anything you want.
Okay. So anyway, it's really interesting because it's all these things that we completely take for granted now. It's really, it was basic, fundamental, exciting research then. And of course, we could go a little bit further and say that this work is kept going, and 10 years later, Jeff Kimball, in his beautiful PhD thesis, did anti-bunching, okay? And it showed that basically light fields can pretty much have any intensity correlation functions that you want, depending on the circumstances. This was done in resonance fluorescence. With Jeff. Are you going to talk about this? In passing, okay. All right. So beautiful, and at this point, people started to understand really how you describe optical fields, and also understood that you actually need to do that. At least you do it best by using coherent states and the techniques that Roy had invented and developed and taught us how to use. So this was really a fantastic time. By the way, I should say that the same thing works in matter wave optics. And this is another thing that I wanted to say, that one reason why matter wave optics and BEC theory has worked as well as fast as it could is that we could import a great deal of the work that we've learned from quantum optics to bosonic systems, for instance, to do the same type of experiments. And just to show you how it can work, this is an experiment done by the group of Alain Aspect in Paris, where they used both metastable helium-4, which is a boson, also helium-3, which I'll show in a minute, which is a fermion. And here are the intensity correlation functions for bosonic helium in an experiment changing the temperature of the sample. And you saw very, very beautifully how you go from a thermal distribution, very much like thermal light, to a coherent state for the bosonic field in a BEC. And they also showed that with fermions, instead of having bunching, you get anti-bunching. So these same ideas work for any bosonic field, essentially. And I'm still convinced that if we had not learned all these tools from Roy's work, we would have struggled many more years before understanding these kind of results. Okay. So let me switch to a slightly different topic. Now I'm going to switch to detectors. Okay? Because it's not just one thing to describe the field, you also have to understand how to measure it. And this is another point which was already in Roy's original papers from the 60s. So basically, he told us we need to understand how we measure these downlight fields, and so we have to have a model of a detector. So he made a model of a detector, and it kind of went out of his area of expertise because he went from harmonic oscillators to two-level systems. And, you know, these are two different groups of people. But anyway, he decided, let's do a two-level system. And went on a limb there. And he said, well, my detector is going to have a light field coming here. And then it's going to be absorbed by the light and probably go to a continuum and eject an electron, right? And there is a theory, and I told you I would not really show you a lot of equations. But the key point is that he showed that what you measure when you do that is that you measure the normally ordered correlation functions of the field, okay? And this is something which was, again, a very key point in this business because it works by absorption. Absorption leads to normally ordered correlation functions. Right, and then he also showed what happens if you have two detectors like a Hanbury-Brown twist to measure intensity correlation functions, which also need to be normally ordered, and all this beautiful work. But Roy said something very interesting. He also said that this is not a realistic model of a detector. And people at the time probably believed you, right? Because, I mean, who has the detector with just one atom? Really. Yeah, detector is probably 10 to the 23 atoms or something. But then there were people who said, really? Okay. And the people who said really are the people who do cavity QED. And we will have a talk by Serge about that. And if you do cavity QED, your detector is a single atom. Okay. So here is an example which is actually from the group of Professor Walter. It's an old picture from 1990 of a micrometer. Just in case you don't remember how a micrometer works, you have an extremely high Q single-mode microwave cavity with a quality factor of maybe 10 to the 10, or an absurd number like that. And you drive this cavity, you pump it one atom at a time, and you can build the light field inside this cavity. Okay? That's one way to operate a micrometer. And how do you measure the field? You don't have good photon detectors in the microwave regime, so what you do is you try to learn something about the field by measuring the atoms after they exit the cavity. So in this sense, your detector is a single atom. And here is an example. So you have your atom, it goes into the cavity. Maybe you've tried to prepare some kind of a field. You send an atom, and you measure the state of the atom after it exits the cavity, and you try to infer the state of the field from this measurement. And this is, again, from this paper by Gerhard Rampe, which relates the Q. This is the Mendel Q function, okay, which is n squared minus n squared over n. And you relate this Q function for the atoms to the Q function from the field. So you use single atoms as detectors, and you learn something about the field. And here's an example of what they saw in one of the situations where a micrometer was creating sub-Poissonian light. Okay. So at the time, I was also working a bit on micrometers, and we actually tried to simulate what happens if you have a series of atoms coming, and your atoms can come out either in their excited state or in their ground state. And from this measurement, you infer what happens to the field. And because you have very, very few photons in the field and you are just at one atom, a measurement on a single atom has a huge back action on the field. So this is just to show you an example of what we did. Gee, it's 30 years ago. Where you would actually have a sequence of a measurement record, and from this measurement record, you infer what the light field inside your cavity does, and you can compare it to what would happen if you just do the mean expectation value result, which shows the back action of the measurements on these systems. So suddenly detectors became very, very important in quantum optics, and in particular the back action of the detectors on whatever system you were looking at. And I'll get back to that in a minute. Okay, so this was Roy's attempt at doing two-level atom physics, but he came back to his senses, and he says, I really don't like two-level atoms. I really like harmonic oscillators. So he realized that if he has a detector which is consisting of many, many atoms, and that not too many of the atoms get excited by the field, you can really describe them as a harmonic oscillator. Okay? And there is this is the best reference I found. I don't know if, did you publish that any other place? Don't remember? Okay. But anyway, so basically he said, well, my detector is really a harmonic oscillator, and life is good again, right? I no longer need to worry about this down two-level system. And of course, what you can see is that if you have a very broadband field, this here, the B case describes the modes of the light field. The A is the harmonic oscillator, which simulates the atomic detector. And you can see under some conditions, this looks like a reservoir. And Roy did quite a bit of work on that, and we'll get back to that in a minute. But then there are the Serge Haroche of the world that say, I don't want to have a sum over K. I just want to have one K. Okay? And this is what cavity QED does. And if you do cavity QED, you get rid of this sum over K, and you get this Hamiltonian. And this is a Hamiltonian which has become extremely fashionable in the last few years. It's the so-called beam splitter Hamiltonian. Okay? And what this beam splitter Hamiltonian allows you to do, so I'm moving back forward in time to the last couple of years, this Hamiltonian actually allows you to do quantum state transfer between two bosonic modes. And it can be used in all kinds of applications. And if you are a fast talker, you can even talk DARPA into giving you money to work on that. And some of us are fast talkers. So here is an experiment which was, wait. Yeah, this is just to explain how this beam splitter Hamiltonian goes. Okay, you can, if you just solve the Heisenberg equations of motion, you find that for the proper time, A and B exchange roles exactly. So that's how you can do state transfer in these systems. And these are some of the key references here. There are now a ton of references on this, but these are, if I had to recommend only three references to get into this business, these are the ones I would actually recommend to my students. The beauty is that now it's been actually done in experiments. This is an experiment that was published just last year by the group around Cindy Riegel and Konrad Lennart at Gila. And what they have done is that they've used this basic state transfer Hamiltonian to transfer a state between an optical field and a microwave field. Now, how do they do that? You can't do it quite directly because, you know, electromagnetic fields don't interact directly. So what they did is that they did something very, very clever. They used a mechanical membrane to couple the two fields. And this mechanical membrane is coupled to the optical field by radiation pressure. It's tiny stuff, it's picograms. So the radiation pressure for the field is going to make this membrane oscillate. But so will the microwave field. And so the microwave field and the optical field are actually coupled by these membranes that they both share. And you can show under some circumstances that this actually becomes a state transfer Hamiltonian, which allows the transfer of a quantum state between an optical field and a microwave field. Now, to be honest, so this is so-called optomechanical coupling. To be honest, they've not yet, as far as I know, done this at the full quantum level. They claim in their paper that they will be fully quantum if they can cool the system a little bit more. They work in cryogenic environments. But there is another paper which has been submitted to PhysRef letters. That's and it's microwave to microwave, so it's two microwave frequencies. This is by the group at NIST in Boulder. And I think, if I recall properly, that they are pretty much at the quantum regime. You can correct me, Jeff, if if I'm wrong on that.
Has this been accepted?
It's such a bad paper, I did not bother to put it here. Right. It's not been accepted, but I'm not holding my breath too much. Okay. Anyway, so this is really fantastic stuff that these people are doing. So this detectors theory, when you go to cavity QED and single mode theories, opens up again the way to fantastic new physics. Okay. So what am I going to talk about too? Now I've looked at detectors. Now I'm going to work on amplifiers. I'm going to tell you what Roy did on amplifiers. It says I've had 23 minutes here. That's what my computer tells me. My computer doesn't lie. Okay, let me talk about amplifiers. 24 minutes now. So, again, this is the beam splitter Hamiltonian, okay? And it has this business where you can exchange a quantum between two bosonic modes, but what you can do is you can change it into a parametric amplifier. And the only way the way you do it is that you just put a dagger, okay? And for a theorist, it's really easy to do. Okay. And if you do that, you get into another problem that Roy worked on very, very early on, which is the parametric amplifier. And I should actually at this point mention that Louis Zell, Yariv, and Sigman worked on that even earlier. These are also very beautiful papers. Both papers should definitely be on everybody's reading list. But here I show this very nice picture of Roy because it shows if you start from a nice coherent state, this is a P of alpha representation. Because of the noise associated with the amplification process, you broaden your distribution. And this will become very important in a couple of minutes. Okay. Another thing that he mentioned, this is really kind of funny, because this is right out of his paper, okay? I did not do any work for this talk, I just copied stuff. And he has this paper with delta p squared and delta q squared, and a beautiful sentence which says, in the examples of this paper, which correspond to Gaussian characteristic functions, p of alpha does not exist in the shaded areas. And the shaded areas are precisely the areas where you have squeezing. So he was really getting into squeezing right there already, except he didn't use the word. Okay. But anyway, parametric amplifiers are very important, and parametric down converters are just as important because you can create entangled photons. These days, these are very important. This is a pretty picture of entangled photons. Because of the polarization uncertainty, if you have a photon coming here or here, it's a superposition of photons with polarization vertical and horizontal. And this is something which is very much used in quantum information science, in tests of Bell inequalities and things like that. I'll get back to that in a minute. What I wanted to say, though, that you can also do that in atom optics, because it's the same equations. All right? But getting back to optics, there is this man. Okay? And who knows this person? Not the old guys in the back. Anybody knows him? This is John Bell. Okay. He's a very, very famous man, John Bell. He's the Bell of the Bell inequalities. And he came up with this fantastic test to see if quantum mechanics was local realistic and all these things. And these tests these inequalities have been measured for many, many years, since the 70s, late 70s, early 80s, late 70s, right? But one of the reasons I bring that up is that there are 3 fantastic papers this year which have pretty much killed any attempt at saying that quantum mechanics doesn't work. One of them was just published a couple of months ago in Nature, and we have 2 of them in PhysRev letters, which are actually much better papers. No, they are much better papers because this is a 2 sigma measurement And this one, which is the Vienna thing, is a 9 sigma measurement, and this is a 7 sigma measurement. So these are really fantastic papers. I mean, all three are great together. But anyway, these papers really prove that all these attempts at the local alternative to quantum mechanics, pretty much you can put the nail on them. Now, the point is that two of these experiments, at least, use entangled photons to do their measurements. Okay? And the entangled photons are produced by these parametric systems that I mentioned. And this leads me back to Roy. So we're going to go back in time. And Roy wrote another wonderful paper in the New York Academy of Science on amplifiers, attenuators, and Schrödinger cats. And he talked actually quite a bit on Bell inequalities in this paper. And basically, he was worried about some results due to this beast here, which is a laser gain tube. Do you remember the laser gain tube? And here is text right out of Roy's paper. He says, a new and interesting suggestion have been added to this picture by, I think it was Nick Herbert. And here's some great things. He adds an amplifier to the system, which he calls a laser gain tube, which you will recognize, this is beautiful Roy language, which you will recognize as a characteristic, innocent and passive sounding name. And he uses another well-chosen term for its action. It clones the photons. Okay? It's wonderful. So Roy said that I need to figure that out. And he did a beautiful full theory of this system dealing with the quantum noise and showed that because of these parametric amplifiers, you can't clone photons. But let me just tell you a few more things since I'm only at 30 minutes. So we talked about his detector, right? That was Roy's detector. And Roy loves harmonic oscillators. He said, I'm going to change this detector into an amplifier. And the way I'm going to make it into an amplifier is that I'm going to change the mass. I'm going to make an oscillator with a negative mass. And if I have an oscillator with a negative mass, then this becomes an amplifier. And you can make a system, I'll get back to that, with inverted atomic systems. And here is this amplifier. Okay, that's again this paper. So I remember the first time I heard Roy talk about that was in Poland. We were at a summer school in Poland. And he really liked that because, of course, the spectrum of this system is like that. And he said, I really like to talk about this in Poland because in Poland everything interesting is underground. I remember that. Of course, this is also a bomb, right? Which relates to your work at Los Alamos, probably, I don't know. But anyway, it's a bomb, but it's not going to make it blow up completely. And you can solve this problem. This is a beautiful model of an amplifier. And again, he showed that Nick Herbert's theory was never going to work because it's going to have so much quantum noise that you cannot really clone your photons. What I like about this paper is that it's a beautiful pedagogical example of something that has been known actually for a little bit longer, which is called the non-cloning theorem, which was published by Wouters and Zurek in '82. But this was a very, very nice concrete example of what can be done. And it turns out these negative masses are interesting, okay? And they've, again, coming back to the present, these masses are very much in fashion, and they are very much in fashion because of quantum measurement back action. So let me remind very briefly how quantum measurement back action works. If you want to measure the position of some quantum system with some accuracy, you're going to impose some uncertainty in momentum. And if you want to make a second measurement after that, this momentum uncertainty is going to come and bite you and increase the uncertainty for the next measurement, right? This is kind of quantum measurement back action in a nutshell. And this is something that people hate because you really want to make very precise measurements. So there have been some very interesting suggestions made just the last couple of years to use negative masses to deal with that. So we are back to these negative masses, okay? And there are three papers that I always have to pick just 2 or 3 papers, but there is a paper by the group of Jean Polzik, actually, there are two papers by Carl Caves. I only listed one of them. And then there is a very nice detailed paper by Ash Clark that just came out a couple of years ago. So the idea is very, very simple. We have a harmonic oscillator. Okay, this is a mechanical harmonic oscillator which is coupled to a light field, and there is some force which changes the position of this oscillator. And then this position is also coupled to the light field. So by looking at the light field, you will get some information on the position. The problem is that once you get information of position, you will have a back action, as I explained earlier, which will change what happens at the next measurements. So what these fellows have said is, let's add a second oscillator, and let's make this oscillator an oscillator with a negative mass. So you see there's a very important minus sign here, and there's a very important minus sign here, and now this force acts on both oscillators. And now you can write the Heisenberg equations of motion for this system. It's not very hard to do. And you introduce these new variables, which is the sum of the positions and the sum of the momenta and the difference of the position and difference of the momenta. And you find that this Q and this pi commute, and this P and this phi commute. So you can create a subsystem of your quantum system which is actually behaving classically. And what you find is that the equations of motion for Q and pi are as written here, but since that Q and pi commute, so you can measure pi as much, you can do that as much as you want, and you will never have a back action. The back action is already put on the other subsystem that you don't care about. Okay, and these things, okay, this is just a little scheme. He's starting to look at me with some nasty eyes, so. But I still have 5 minutes and 9 seconds. So anyway, this is really what happens here. If you have your systems A and B, you have back action, and you measure a phase shift and have a back action. If you use this combined system in just one of the subsystems, you can measure the phase shift and put the back action in a place that you don't care about. So your negative masses, Roy, are back in play, and this is actually being demonstrated in experiments as we speak. So, and the way you make negative mass systems is inverted atomic systems, as you had guessed. So, let me summarize before John kicks me. That's my summary. If you look at quantum optics, we do it today. I mean, Roy's fingerprints are everywhere, okay? It's really extraordinary what he has done. It's also extraordinary what we have learned in 50 years. I mean, from not knowing how a laser works, having all kinds of crazy, wrong ideas, to able to do these really exquisite experiments that people are doing now, is just fantastic, and it's to a huge part thanks to you, Roy. So thank you very much.